Let me know once you're able to. I think you're able to see my screen, right? All right. So this question that we were doing yesterday, BST Iterator Part Two. I hope you were able to find this problem. On bunch of website it is there. If you just type BST Iterator 2, you will get it. And I did share the link as well yesterday. But let me share it again if someone doesn't have it, just in case. BST Iterator 2. So I think this is the Code Ninjas one that you can give it a try. So let's use this link to implement the approach. And okay, so idea about this problem is that we want to, along with the next, we also want to have the previous, right? So we have to implement the iterator class. In the We already did the first part of it, in which we just had to implement the next, and we did not had to implement the previous part of it, right? But in this case, now we need to implement the previous as well. So the idea that we were discussing yesterday to handle it, the idea is that we are going to use a combination of, we are going to use a visited list or an in order list. We are going to form along with the stack. So yesterday when we were doing this problem, we had done it with the approach of using a stack, which is our in order depth DFS traversal data structure that we were using. So just to refresh things a little bit, what we were doing is we were pushing. So basically, in the in order traversal, what we do is we traverse we start from a root node, and then we keep on going to the left as till the left branch is there, and we keep pushing. And in this approach, we use a stack. We follow the similar approach. We push the root node onto the stack, and then we keep pushing the left child onto the stack until there is no more left child available to us. And so you can say that the leftmost child or the leftmost node in the tree will be at the top of the stack once we do that. So we're going to use the same approach, and whenever the next has to be called, so we pop an element from the stack. This is going to be the next element. But after popping the element from the stack, we also check if this has any right tree or a right children, or along with that or not. If it has any right side branch, we gonna switch to that right side branch, and we start pushing all those right side, right the right side children, and its longest left branch into our stack as well. So that we, because in the in order traversal we want to finish everything belonging to the left side node. So if it has any left, all the left side branches are already covered with the way we have pushed the items on the stack, but the right side branches are not yet covered. So whenever we pop an element from the stack, we check if it has any right side children or not. If it has any right side children, we switch to the right side branch, and then we again do the same process that we did with the root node. So we keep traversing to the left and keep adding all the elements on its left side branch to the stack. So that step remains exactly the same, no changes in that. But one thing that gets added as part of this particular thing is that um, we have to keep a track of the previous as well. And when we do a previous, the pointer should move to the previous element that we had, or the predecessor node. So essentially, in this case, if you do a next, it should return you 3. If you do a second next, it should return you 7. And if you do a again next, it should return 15. But when you do a previous on 15, like let's say the current pointer is set to 15, if we do a previous here, we should get back 7. And if we again do next on 7, we should again get back 15. So we should be able to go back and then go front from there. The way to handle that is, Yesterday, I was thinking around one possibility that we could remove, and when we are removing the items from the stack as part of the next, as part of get next operation, do we should is it a good idea to move the when we do a previous, is it a good idea to move the items into the stack again? So first of all, there is no way to keep a track of the items which were previously visited. The reason is that, let's say if we try to build a stack, let me first share my thought process. So if we try to build a stack over here, in the stack we are going to push 7 into the stack, then we are going to push 3 into the stack, right? This is the initial state of my stack. Then 3 is element at the top is 3, like at the rightmost element. So first we gonna, when we say next, 3 is going to be popped from the stack and it is going to be returned. And then we check if 3 has any right side children. 3 does not have any right branch, so this is left as it is. But when we again do a next, 7 will be removed and returned. But before returning, we will be checking if 7 has any right side branch. 7 actually has a right side branch, so we're gonna be removing, we'll be adding 15 back to the stack and all its left children back to the stack. So 15 only has one left child, which is 9. So 15 and 9 goes back to the stack as part of removing 7 from the stack. So now at this point of time, if you do a next, you definitely get 15. But instead of doing next, if you do previous, like for example, we do next and we get to 15, right? And again, if we do next, we will get 9. But uh, but after going to 15, if we try to do previous, there is no way we can get back 7, because 7 is not a child of 15, it is not a descendant of 15. So there is no way that I can just get 7 by using 15 again. So I need to keep track of all the elements or the nodes that I we need to keep track of all the nodes that we have previously visited as part of our in order traversal. So what we're going to do is, at this point of time, we're going to keep track of all the nodes that we have previously visited as part of the in order traversal. So whenever we are doing next, whenever this next is being called, uh, and before moving the pointer, or before changing the top of the stack to the next element, we are going to be saving the element, the previous top, into a data structure, so that we will keep a track of the history of all the in order nodes that we have visited so far. So what I mean to say is, we already visited 3, then we already visited 7, and now we are visiting 15. So we will be keeping a track of the list as well. So the list is going to contain 3 and 7. So initially the list is going to be empty, it does not contain anything. The stack is going to contain 7 and 3, where 3 is the top of the stack. So when you say next, 3 will be removed from the stack and 3 will be pushed into the list. Okay. And we will also be maintaining a pointer into the list. I'll tell you the reason for it, why do we need it. But the pointer is going to tell us, like, or you can say that an index we will maintain into the list. This index is going to tell us what's the latest element that we had already visited. So the latest element is the 3, so the index is going to be 0 at this point. So once we have inserted 3, the index will be 0. So initially the index will start from -1. So just to again make it very very clear, initially the index will start from -1. It means that we haven't visited anything as of yet, and the list and list is also empty at this point. So when we pop an element from the stack, like when we do a next operation, 3 is going to be removed from the stack, 3 is going to be added into the list, and the index is going to move to 0. It means that the current element, or the previously visited element is present at the index 0. Then we're going to remove, when we do a get next operation, two things we are going to see. First, we are going to see is that, is index plus 1, so is this index lesser than the size, like is this the last position in this list or not. Basically that's what we are going to check. If this index is referring to the last position in the list, so here index value is 0 and this is the last position in the list. So if index is referring to the last position in the list, it means that we don't have any cached items in the list which are not yet visited. It means that all the items in the list have already been visited. It is already pointing to the last element. So it means that the next element has to come from the stack. So then we pop an element from the stack. So 7 will be popped from the stack and added to the list, and this index is going to be is going to be moved to 1. But while removing the element 7 from the stack, we also check does it has any right side branch or not. It has a right side branch, so 15 is the element starting from the right side branch. Then we visit its right side branch and keep adding all the elements on its left side branch, just like the usual process that we do. So we add 15 and 9 into the stack. At this point of time, your index is the index in the list is pointing to 1. It means that we have already this is the last item that was added into the list, or the last item that was visited in the list. So now let's say we have to do a next at this point of time. When we do a if a next is being called at this point of time, we are going to check is this index pointing to the last element, or is there some further cached elements, are there some further elements in the list which aren't yet visited. So since this index is referring to the last element, it means that all the items in the list have been visited, so we have to get the next element from the stack itself. So we get the next element from the stack, which is 15. Which is not 15, which is going to be 9, because 9 is at the top of the stack. So I'll be removing 9 from the stack. I'll be adding it to list and putting my index equal to 2. Since 9 does not have any right side branch, so we'll not be adding anything back to the stack from this value 9. Now imagine at this point of time, if we happen to call next, we will be getting 15 right at this point of time. But if we happen to call previous, right, so what should the previous return us? If someone So if we take this example, right, example number 1. So when the initially next is called, 3 is returned. Then when second time next gives us 7, uh, third time the previous is being called. So we are already, like, we already have popped 7 from the stack and added to the list. But when you do a previous, you do not return 7 back, you return 3. So which is logical to understand. But so just in case here as well. So when you do a next, you return 15 and you return 9. So and you added 9 into the list, okay. But when you do a previous now, your index is already pointing to 2. So it means that this is the latest item that you visited. So when you do a previous, you would want to return one index before this. So the previous item, so it should be 7 and it should not be 9. So this will be returned as an index is going to shift to 1. So you will return 7 from the list, because list is going to contain the order of all the items that you have visited before. So the previous item is going to be 7. Now at this point of time, if you do a next, we are going to check is this index already pointing to the last element. This index is not pointing to the last element as of now. This is pointing to the middle element. So it means that there are some elements over here which are pending in my Inorder traversal, because I had shifted my current pointer using the get previous operation. So I had shifted my current pointer uh, in the middle of the list, somewhere in the middle of the list. So when you do a next, I'm not going to pop an item from the stack, because this list is still having some leftover items. So I'm going to be moving my index one position to the right. when I move it to the 2, so it means index is going to become 2, and the element at index 2 is going to be returned as the next element. So the next element will be 9. After this, if I happen to do a next at this point of time, the next is not present in the list, so this element has to be fetched from the stack, and at this point of time 15 is going to be popped from the stack. It is going to come to the list, and this index is going to be incremented to 3. And after removing 15 from the stack, we also check if 15 has any children, right side children. It has a right children 20, so we add 20 back to the stack. And yeah, and at this point of time, if you do a next, the next will be 20 again. Next is going to be 20 because we are already pointing at 15, which is the last element in the list. But if you do a previous, the previous is going to return a 9 because the previous item is 9. Is this dry run, or this computation is clear to everyone? Anyone who is not clear with this or has some doubts in this? Okay. uh Palak, is this clear? All right, so let's move on to the implementation. Implementation is going to be really simple, just as what we discussed. So what we are going to do is we are going to take a stack here, similar to the previous one. We are also going to take a list. I'm going to call this list the in order list, so as to make sure that the variable names are meaningful. I'm also going to initialize an index which is going to keep track of which position in the list is my current position. Okay. So this in order list is the list of items that we have already traversed, and we have formed this in order list so far. So please note that we are making it on the go. We are not pre-computing it completely. So we discussed the one of the solutions yesterday for this problem was a naive solution is that you can do a in order traversal. You can compute this in order list completely, which is you can say a eager. So there is like a two ways of initializing a data structure. One is like a lazy initialization. Second is like a eager initialization. Initialization is when you compute it fully as a first step. So you can compute this entire thing in the constructor by calling the inorder recursive method, or inorder recursive approach. And then whenever there's a next is being called, you can just maintain a point, maintain an index, and keep, and using that you can just simply return the next or the previous item. But that approach, first of all you have to compute it completely, and it is a recursive based approach. The second approach is where we are doing a partial computation depending upon when this next and previous is being called. So for that we are creating this in order list over a period of time, like we are creating it as we go. It may also happen that this entire tree has millions of nodes, but this next is going to be called very few times, for example, right? So in this kind of use case, this approach is very much helpful because we are not, when we are initializing our stack, we are just going to, this is going to be initialized with the left side branch. So at most the height, the size is going to be the height of the tree. So having said all of that, let's initialize everything. So I'm going to initialize this index as -1 that we discussed. So this index is going to tell us what's the latest or the last element that we have visited so far. Currently we have not visited anything, so I'm going to initialize it with -1. The second thing, I'm going to initialize my stack as empty. I'm also going to initialize my in order list as an empty list. Okay, and then I'll also push all the left side branch into my stack to begin with. So I'll say that while root is not equal to null, so stack dot push root, and root is equal to root dot left. So this is like the standard stuff that we did yesterday also. Now when we are doing a has next, we'll do a has next on two bases. First thing is we can check if the stack is empty or not. So we can say that return if stack is not empty, so it means that it has some elements left. Or even if the stack is let's say the stack is empty, but we have already let's say we have exhausted all the elements in the stack, right? In this case also, let's say if 20 on 20 also we do a next after this, so 20 will be pushed into the list, right? And then the stack becomes empty and index will become 4. But it can possibly happen that a previous is being called now. So instead of doing a get next, the from the, let's say the previous operation is being called at this point. If a get previous is being called, then the current pointer will shift to 15, and 15 is going to get returned. And at this point, if a get next is called, even though my stack is empty, I do have I do have a next element remaining in my list, which is 20. So I can still return my answer because my current pointer has shifted to somewhere in the middle of the list. It is not at the end of the at the last element of the list. So for this purpose, I'll be checking either if my stack is not empty or my list has still some elements left over. And how to do that? So index is always going to point at the last element, inserted last element or the current element in the list. So if this element is the last element itself, so I'm going to check that if index plus 1, if this let's say if this is actually lesser than my size of the list. So if this is the case, it means that there is that this is not yet the last element. There are still some more elements remaining in my list uh, that are in order successors for this current element, and that we can return. So if this is the case, or if stack is not empty, then it means I do have the next element remaining. And to give the next element, what we can do is first we can check like this is the very first thing that we can check before checking anything in the stack. So I can check, so index, I can either do an index plus 1 or I can do an index plus plus. In either case we have to increment the index, but fine. So I can first check that if index plus 1, if this is, let's say if this is the last element, right? If this is the last element in the list, if index is already pointing to, so assume that if index is already pointing to 0 1 2 3 4, if index is already pointing to 20, so its position is 4. So this is already the last element in the list. And if this is the case, in this particular case, I know that I don't have any further elements left in the list. So we should be popping an element from the stack, and we don't have anything to get back from the list. So this is the first condition that I'll be checking. If index plus 1 is equal to list dot size, then it means that no more elements in list. So pop an element from the stack. Okay, so this is the this is what we'll be doing over here. So first thing we will be doing is I'll be popping an element from the stack. So stack dot pop, and this is what we need to return. So I'm just capturing it in the result directly. Then after we pop it from the stack, we also have to add back, we also have to add if this node has any right side branch. So I'm gonna say that, let's say if it has any right side branch, result dot right. And I'll say if while current is not null, then keep adding stack dot push current, and current is equal to current dot right. Okay, so we can check if it has any leftover uh, if it has any leftover elements in the branch. So after doing if it has any leftover right side branch, so after doing all of that, now the next thing that we should be doing is, can you tell me what all I should be doing after this point? we have added all the elements from the stack, we have popped the required element from the stack. What should be done here? Okay. Mm, just the pointer. Yes, that's the main thing. So basically the list that we have, what's the name of the list we have? In order list, right? I think I need to correct the names here. So it is in order list dot size, in order list dot size. So here I'm gonna say that in order list dot add result dot val. So I should be adding this uh, to the list, and the index should be incremented to index plus plus. Correct. This is what I should be doing, and then we can simply return the result, whatever is this value that we have popped. So we can return this result dot val. In the else part, if this was not the case, if index plus 1, it means that the list already had some elements left over. So in that case I should be returning the element from index plus 1 position, and then again I have to increment the index as well. So in both the cases, so just to mention, so here we can just simply return the result. We can first of all do index plus plus, and then return in order list dot get index. um, is this part clear? We can simplify this code a little bit, but is this part clear what we are trying to do? Okay, we can simplify this. As you can see, index has to be incremented in both the places, regardless. So what we can do is we can just increment the index at the very top itself. We can do index plus plus, and here we can just simply check index is equal to this. So we can don't have to do index plus plus here and here. Second thing, we have already inserted this element into the in order list also. So instead of returning it from the result, we could just simply return it from the list as well, right? Because in the last also we are returning it from the list, and the same position we need to return, because we added this element into the in order list. So when we so this is a append operation basically. So this will get added at index plus plus, right? The new value of index essentially. So we can combine everything just to make things very simple. We can just remove everything here. We can remove this else block, and we can remove this, and we can just simply return this. So essentially what we are doing is, if this visited list does not have any more elements to return, first we pop an element, we put it into the list. uh, where is that? I think I removed the insertion part, my bad. So in order list dot add result dot val. Okay. So so basically we first insert the element into the list, and then whatever is the last element, um, whatever is the element at the index position, because here we had already incremented the result, the index. So whatever is the index value, we just return the element from there. So we have just simplified the code. Is this clear? Okay. Cool. And for the has previous part, what we can do is, we know that index is pointing to the current element and we have to return the previous element. So we can check if index minus 1 is greater than equal to 0. So if this is the case, it means that it has a previous element. Index is the current element, and if we go to the previous element, the net index should be greater greater than equal to 0. And to actually get the previous element, also please note that whenever the get and previous calls are being made, it is currently given that you may assume that the next and previous calls will always be valid. That is, there will be at least a next or a previous number in the order. But in the interviews, if you have to, before making this call, you can first check like if it has previous, you know. So you can just make this call. If it has previous, then you do the rest of the stuff. Else you can probably like return or throw an error or return some junk value like -1 or whatever. But in this particular question, we don't have to really invoke the has previous, because it is already given that these calls are valid. So whenever these calls are made, there is definitely some previous value. And similarly for the next as well, we don't have to check has next. But in your interviews or in production code, you definitely have first be making a call to has next and then doing the rest of the stuff. Okay. So um so having said that, for the previous, it should be pretty simple. We can just do an index minus minus, and we know that previous element exists. So it means that index minus minus should always be greater than equal to 0. So we can safely go back to a previous index, and whatever is the in order list dot get index, whatever is the value, we can just simply return that. So this is the approach. So we can just simply call this. There is some few things we need to fix. So it's a stack of tree node, not the stack of integer. So mm, let me just check what's the issue here. It's current dot left in line number 47. So we are pushing. You can wrap this part inside a function as well, because you need to do the same thing in the constructor as well. So when you are creating initializing the constructor, you are adding the root, and then you're adding all the left side branches. So this all the left side branch you're adding, and here also you are going to the right side child and then adding its left branch to the stack. So you could just put it into a function and do the same also, but it just 2 3 lines, so I did not create a function for it. Okay, so this passes, and we can submit it as well. Okay, is this question clear? Anyone? um so in the next function, we are doing it at index plus in the very beginning itself. You can do it at, as I said, you can do it at the last also, depending upon your convenience. I It just like the to make the code concise, we did that. So otherwise you could do, I think the first version we wrote was index plus one, and then here you can do a index plus plus, right? And then but in the and then you can write a else part and do the same. So to avoid all of that, we just did it at the very top. So whenever you are saying next, it means that we have to go to the next. If if the visited list does not contain this element, we will be adding this element to the visited list. Okay. So so we'll be adding this element to the visited list if the list does not have this next element, and then we can just return the element from the visited list. uh, can you guys start implementing it, and just let me know once you're done. We'll take 5 minutes to to do this at your end, but meanwhile I'll just copy paste this into the doc. So I'll be back in 10 minutes. Sure, Lokesh. What about others? Are you guys done with the implementation? Um, shouldn't take this much time. Are you guys done? Anya, I'm not hearing anything from you. Manasvi, you're also done? Okay. What about you, Anya? Okay. All right. So let's move on to the next problem. The next few questions are interesting. We'll be building some concepts in those questions as well, and then we'll be discussing. So this is the first problem that we want to do. This problem you can easily find at multiple places in order successor in a BST. It's a premium locked question, but let me find out this problem for you. In order successor in BST. I think it's there in the GFG also, and it's there in the Code Ninjas as well. Let me share the link for the. Is there a practice one for this? I'm not sure. 1 second. I'm just checking. Let me know if you guys are able to access it from some other place. In order successor in BST. I think this should be node X. Yeah, I think this should be one on GFG. So I'm sending the link to you. In order successor in BST. Are you guys able to see this problem? Okay. So the idea, we'll be doing two things over here. For one is we'll be discussing a generic approach to finding a success in order successor in any binary tree. That's the very first thing we'll be doing. And the second thing that we'll be doing is we'll be doing the finding the in order successor using the BST property. So let's first do the BST part so that this question is done, and then we'll discuss a generic way to find a in order in a binary tree. So the property of a BST, as we have multiple times discussed, is that a given node has to be strictly greater than its left child, and it has to be strictly less than its right child. And the tree always contains all unique elements. There is no duplicates inside a BST. That's like the property of a BST tree. And given this property, if we have to find the successor of any given node, so what we know for a fact is that, let's say we have to find the successor of a given node p is equal to 1. Now the successor of any given node can either depends on two things. First, does it have a right subtree? If it has a right subtree, then this successor is always going to lie in the right subtree part of the node. But if the node does not have a right subtree, then the successor is always going to be one of the ancestors. We do not know which ancestor, but one of the ancestors would be the parent. And there can be some cases in which there can be no ancestors, as there can be no in order successor also. Like for example, there is no in order successor of 3. But if we take a look at in order successor of 1, so 1 does not have any right subtree. So the in order successor of 1 is always going to be one of the ancestors. Which ancestor is going to be the one whose whose branch, one is like the left child. So let's say any of the ancestors of 1, uh, if we keep going up and we find a branch in which the child is actually the left child of the parent, then that parent is going to be the ancestor. Why is that the case? So if you can see, one's ancestor is 2, and 1 is actually the left child of the parent 2. So that's why the in order successor of 1 is actually going to be 2. If we take another look, for example 4, if we had to find the in order successor of 4, in order successor of 4 is not 3. And there is no, first of all, there is no right side branch of 4. So in order successor of 4 is and so we have to go to the parent or ancestral paths to check. So in order successor of 4 uh, cannot be 3. The reason is that 4 is actually the right child of 3. So 3 cannot be the in order successor. And if we keep on going to the ancestral chain, the parent of 3 is 5. And now we check, is 3 the left child of 5? 3 happens to be the left child of 5. So 5 is going to be the ancestor of, is going to be the in order successor of 4. Does that, and this is the generic way I'm talking about. In any bind, this here I'm not using any BST property yet, but I'm just talking about in a generic way. So if you need to find a in order successor of any node in a binary tree, so either the in order if the node has a right subtree, the in order successor is going to be the smallest node in the right subtree. Like for example, if we had to find the in order successor of 4, in order successor of in order successor of 3, the in order successor of 3 is going to be 4, because it has a right subtree. But if we have to find in order successor of 2, 2 doesn't have any right subtree. So we will keep on going to the ancestral chain until we find a node whose parent, until we find a parent uh, whose left child is this chain that we are going through. So 2's parent is 3, and 2 is also the left child of 3. So 3 is going to be the in order successor. Similarly, we have to find the in order successor of 6. So if we have to find in order successor of 6, first of all, 6 does not have any right child. So we have to go to the parent. What's the parent? 5. And then we but is 5 is 5's left child happen to be 6? Not really, it is a right child of 5. So it means 5 is not the one. So we have to go further up, but there is no parent of 5, and that will lead us to null basically. So that's why 6 does not have any in order successor. Is this concept clear to everyone? Okay. um so that is like a in a usual binary tree format. Sometimes when we have to go to the parent, generally the parent pointer may not be given to us. For example, in this particular um, use case over here, there is no parent pointer given to us. We have to use a BST property. So let's let me first share my screen, or maybe let's write the structure over here for a generic binary tree. So assume that it's a binary tree and not a BST. Okay, not a BST. So the use case one. So if it is a binary tree and not a BST, in this case, what we'll do is the code is going to somewhat look like this. That we will be first checking if node has a right child or not. If node has a right child, if yes, then for this particular case, if let's say if it has a right child to it, then what we can do is, let me start writing the code as well over here. So let's say that if it has a right child to it, what we can do, assume that the same function is given to us and we need to implement for, let me just call in order successor binary tree. Okay, so in case if the node has any, first we'll check if node has any right child or not. If the node has a right child, if the node has a right child, then in that case, what we gonna do is, we're gonna take a node, let's say the current is equal to p dot right, and then we keep on going to the left. So while current dot left is not null, then we can just keep going to the left until there is no left child remaining, and whatever is the last value of the current, that is going to be the um, in order successor. This is the very first case, if right child exists. Okay, but in case the right child does not exist, we have two options. um, we have two options, like we need to, either we can use parent pointer chain and find out ancestor whose left child, and find out an ancestor whose left child is the and find out ancestor whose left child is the given child, whose left child, how do I put it in words, I don't know. So whose left child happens to be this chain, happens to be this chain. Okay, but in our case, if there is no parent pointer given, we don't have any parent pointer given here, we just have a left and a right. So it means you can only go to the children, you cannot go to the parent. So in this case, we cannot really use, you cannot really take leverage of the parent, right? So in this particular case, since this is not there, since parent chain is not given, then what we can do is, we can simply use in order traversal and keep track of previous node. So how to, what do I mean by that is, we in the other case, I can just simply call over here else, if the right side thing does not exist, then I can just simply call the in order traversal, and I can pass here the root and p. Okay, um and in my in-order traversal, so I can create a function for the in-order traversal over here. Let me just remove this. So I can just create a in-order traversal, and I can keep track of the previous node. So whatever is the previous node, uh, So basically we need to check that whose node p is actually the previous of. So that will be my in order successor. So what we can simply do is, if root, we can just do the same check, return, uh, then in order root dot left, then we can check over here that if and every time we are keeping a track of the previous, so we will be creating over here a previous node. Let's say tree node previous, and we can say that successor. So we can just populate the values. Initially they can start with null, and we can um, populate the values accordingly. um, so so what we can do is, we can check over here that if let's say the previous, what we have done over here, if previous is equal to, if previous is equal to p, it means that the current node that we are visiting in the in order sequence, this node's previous was equal to the node p, or the node that for which we have to find the in order successor. So if this is the case, it means we have found the in order successor. So now we can do a in order successor equal to the current node, the current node that we have, and we can just simply return at this point of time. And otherwise what we do is, for every node we so this route that we are currently visiting, it will become previous for the next one that we are processing. So we assign previous to root, and then we go to the right. So essentially it's a in order traversal we are doing. First we are visiting the left, then we are doing two steps. We are checking if the previous node happened to be the node itself for which we have to find the successor. It means that the current node itself is the successor. So we assign this to the root and just simply return back here. And otherwise if that's not the case, then this root, this current node that we are visiting, will become the previous for something else. So it will become the previous for the next one, for the next iteration. So we are assigning the previous, the current root as previous, and then going to the right side child. And yeah, and that's all. So at the very end of it, once this iteration completes, then we can just return the in order successor from here. You can just return successor, and like, you're populating this value here. Is this part clear to everyone, what we are doing to find the in order successor for a binary tree? Anyone who is not clear with this concept, you should know how to find a in order in a binary tree. And you should, I mean, the in order successor in a binary tree. Interviewer might twist the question that instead of BST, let's say he first ask you the BST, but then he say, oh, what about the binary tree? What will you do if it's just a binary tree? So right now we have discussed it for a binary tree. I discussed the two cases, two scenarios with you. If the right child exists, then it's a very simple case. If the right child exists, then you just simply go to the right child. It means your successor is going to be there in the right subtree, somewhere in the right subtree. So you have to find the smallest node in the right subtree. Not even the smallest node, you can just say the leftmost node in the right subtree. So that's what we are doing. So if right child exists, find the leftmost node in right subtree. Okay, but otherwise if it does not exist, then there are two ways. One is, if the parent pointer chain is given to you, we'll see this in our next problem. So there's a BST part 2, in that the parent chain is given. So if the parent chain is given to us, we can just keep on going to the parent till the time, I think we wrote the concept here, right? We can keep on going to the parent pointer until um, till the time we have found a parent whose left child happens to be this chain. So so the child whose parent we are searching, if this child happens to be the left child of the parent, then the parent is the in order successor. And we saw that using a couple of examples as well. But in case the parent pointer is not given to us, then we have to use the in order traversal and keep track of the previous node, which is going to be our um, keep track of the previous node. And if the previous node happens to be the current node, then it means that the current node is a successor. So we just assign the successor and return, and you can use it as a global variable, which you can just set it up and just return it. So I hope everyone is clear with this. So coming on to the question of so let me just comment this whole thing out, since this is not a part of the this is not the part of the question that's being asked to us. And now we'll talk about the BST part. Okay. So what if since here we are not using the BST property, now this tree is given as a BST. As we already know the properties of BST, so what we're gonna do is we're gonna say that in using the BST property we can also find it out. So what we are going to say, we know that successor node is always going to be higher than the current node that is given to us. So if p is equal to 1, we have to find successor of 1. So 2 is going to be the successor, for example. So what we're going to do is we're going to start from the root, and if this root happens to be greater than the value that we are looking for, then we will make this root as a potential successor and then keep going left, because we are looking for a let's say the closest successor, right? The closest value which is higher than 1, that's what we are looking for. So for example, let me take this bigger tree as an example. So let's say we have to find the in order successor of 3. The in order successor of 3 is actually 4, right? So to do that, we start with from 5. We check that whether 5 is greater than the 3 itself. If 5 is greater than 3, then we'll mark it as a potential successor. Then we move to the left side of the tree. Then we check whether this value is still greater. This value is not greater, so this is 3 itself basically, but so it is not greater than the 3. So it means that the in order successor cannot lie in the left portion of the tree. So if we are already at 3 and we are looking for the in order successor of 3, and 3 itself is equal to 3, right? So we the successor has to be strictly greater than the value that we are looking for. So we have to go into the right part of the tree. At this point of time, the in order successor remains as 5. Now does the right part exist? Yeah, the right part exists, so we go to the right. It happens to be 4. Now this 4 is as it is greater than the value 3, so this is the next potential in order successor. But now this is greater than the potential value, then we are looking to minimize it, so we'll go to the left. Is there any left child of 4? There is no left child of 4, so we stop here, and this is our answer. Just to reiterate it again, imagine that 4 was not there in the picture, then we would start from 5. 5 is the potential successor. We Since 5 is the successor and 5 is greater than 3, so we should not be moving to the right of 5, because 5 is already the answer, and towards the right of 5 all the values will be greater. So they cannot be the answer, they cannot be the in order successor, because we are marking 5 as a successor and all the values are greater than 5. So we have to find the nearest value to it, so we'll go to the left. We go to the left, we find 3, and but 3 is same as the node whose successor we are trying to find, so this cannot, so it means we cannot go to the left. We'll try to go to the right, but if there is no right subtree, then 5 will be returned as the answer to start with. Is this logic clear to everyone? about the using the BST property to find the in order successor. Okay, so this is pretty simple. So we'll just write the code. We'll let me let me write the code for it, and we'll just fix this as well. So to find the in order successor of this, I'm gonna take we can assign the in order successor as null to begin with, and we can say that while root is not null, uh, if in the case if root dot value is strictly greater than the p dot value. Okay. uh, so if root dot value is strictly greater than the p dot value, it means that we have found a potential successor. So root can be a potential successor. So we're gonna assign the successor to the root, and then will be and we know that since root is a potential successor, we anything towards the right of the root cannot be the successor now, because they will be much higher than root. And so we have to go to the left. So I'll be saying root is equal to root dot left. In the else part, what happens is the root value is lesser than or equal to the p's value. It means that the current node value is either less than or equal to the node whose successor we are trying to find. Since uh, it's smaller than or equal to, it means we should not go to the left subtree, we should only go to the right subtree, because successor can only lie in the right subtree, as all the values in the left will be smaller. So we just simply gonna go to the root dot right, and at the very end of it we can just simply return the successor. Is this piece clear, what we have done? Any Okay, so let's run this code then. So this passes, and let's submit it, and let's also do a bit of a time complexity. Can someone talk to me about what should be the time complexity for this? Mhm. Okay, can you be more specific? That's a generic thing. Yeah, in worst case it will be the height, but then be more specific. What will be the actual time complexity? Because that will tell us if you really understood the algorithm or not. So take this case. Let's say we have to find the in order successor of 3. What chain are we visiting as part of this algorithm? uh, that's okay. That's what Palak also mentioned, height of the tree. But what I'm asking is, I'm not asking that. That is evident. It is equal to the height of the tree. So if it's a skew tree, then height is n at that time. But what I'm asking is, let's say if a tree has thousands of nodes, but the node that you're trying to find is present at the second position. What I'm asking is what all sequence of nodes gets visited in this tree when I have to find the in-order successor of three. What is the sequence of nodes that get visited in this? Why are other people silent, Tejas and Manasvi? Are you not understanding that? So what is the sequence of nodes that get visited? Let's say for three, we have to find out in-order successor of three. What is the sequence of nodes that are like visited when I run this algorithm? Correct. And do we visit any other nodes apart from 534, right? So the time complexity is actually going to be the length of the node starting from your root, the length of the target node of whose successor you are looking to find. So length of the node, length of the tree, you can say the length, the branch length starting from root node going to that target node. And if the target node has any right side branch, then you go to the right side branch and then go to the left. Like let's say 4 had again the left children. You know, for example, let's say 2.5, 2.4, 3.5, 3.3, some values are there in decimals. So we will be visiting that branch also. So mm, just to be very more specific, the branch that you're visiting is starting from the root all the way up to the target. And if the target has any right side branch, then you go to the right side branch and then keep visiting, then keep finding the leftmost element in it. So that is like the visit, the maximum number of nodes that you would be visiting. So yeah, in the worst case, it is going to be the height of the tree. So whatever is the height, and when will the worst case happen? The worst case will happen if the height, the maximum depth, is being formed using this node, the target node, and either it's the last element in that target node, or this lies in between the biggest branch, but it has the right side branches to it. If 3 did not have any right side branches and if only the left side branch was there, we would stop at 3 itself, we would not visit 4. Okay, so yeah. uh, so just explaining what is you should be like when you're solving these problems, you should also be just spending a little bit more time what is the sequence order in which the branches are visited. And in that case you can go, if interviewer happens to ask you little more detailed in depth that like this is the scenario xyz, you have 100 nodes but you only have the desired node is present at third index or at the third or at the second level, for example. So let's say there are 1,000 levels in this tree. So if there are 1,000 levels, the total number of nodes would be approximately, at each level you have 2 raised to power n nodes. So level 0 you have one node, at level 2 you have two nodes, at level 3 you can have maximum four nodes. So level 0, 1, 2, so 2 raised to power n if you're starting from 0th based indexing. If you're starting from 1 indexing, then 2 raised to power n minus 1 nodes are there at each level. So uh, if your node is present at ith level, you have to like basically you're only visiting each level just once, like one of the nodes in the level once. So you would be having at least have to visit at least I number of nodes if it is present at ith level. And then you'll be checking what's the deepest the right side left branch goes up to. So that is going to be our overall time complexity. So yeah, you can say big of edge, big of height, and but then if you wants to go into more detail, then you can put your thoughts. That is going to differentiate you with respect to the most of the people who have just mugged up this thing, and that is going to be like a huge differentiating factor in these rounds. um okay, so going to the next problem. So we'll be doing, let me also just update it in the document, the entire thing. One, give me a second. So we have updated, I've updated this. Cool. Heading to, fine. So the next question that we want to do is the continuation of this problem, which is um, in order successor in BST part 2. So in this problem, basically, uh, it's the same question, but here the parent pointer is given to us. Okay. If a parent pointer is given to us, you do not need a root. You do not need the root of the tree. You can just find the successor using the node itself, whose successor you have to find. You don't need a root reference for the tree. And we discussed this use case, right? If the parent is given to us, first thing we can check if this root has, if this node, let's say the 2 is the, we have to find, for example, we have to find for, let's take a bigger tree, we have to find for 5, the successor of 5, and 5 is given to us. Then we will check if 5 has any right side branch. If 5 has a right side branch, we'll go to that branch and we'll try to find out the leftmost element in that branch. So here 6 is the branch and 6 is the right leftmost element in its branch itself. So 6 will be the answer. So a similar thing goes for 3. So we have to find for 3, 4 will be the answer. But if we have to find for 4, for example, the in order successor of 4, 4 does not have any right side branch. So we go to the left side, we go to the parent pointer, we go to the ancestor chain. How long we have to go up? We have to go up until we find a chain such that the child happens to be the left child of the parent. So first we go to the 3, we check if this chain is like the left branch of the parent. So 4 is the right child of 3, not the left child. So it means 3 cannot be my successor. And the reason is simple, right? Because 3, if this chain is the right side chain, it means that 3 is actually a predecessor. Because if you do a in order traversal, then 3 will be visited before 4, and here you're looking for a successor. So it means that you cannot, you have to keep going up. So now when we go up, we see a node 5, and the child 3, the reference that we came up with, this happens to be the left linkage with the parent. So 5 is going to be my answer. And why is this the case? Just to explain you, this is the case. The simple reason is that it means that parent node is greater than, if it is a left side linkage, it means that the parent node, uh, the first parent node whose linkage in this chain is the left side linkage, this parent is sitting somewhere in the middle. Like this parent is sitting somewhere in the middle, so its left branch is this entire subtree in which our node is there. So 4 is present in this whole subtree of the left subtree of 5. So 5 is going to be the answer. Is this logic clear to everyone? We already discussed it, so that's why I'm just explaining in quick. Okay, can you guys start implementing this? Let me try to find out this BST iterator 2. Yeah, I think we have it. 1 minute. BST iterator. Sorry, this is the uh, what's the question name? In order successor 2. In order successor 2. In order successor in BST2. Algo monster. By the way, how many of you have this membership of the premium membership of LeetCode? That's okay. So you are able to access this problem, right? And what about others? And okay, Te- uh, Tejas, Palak, do you also have it? Okay. Uh, yeah, I mean, it's not really necessary. Only thing is that for these Tejas, you have it. Okay. So I think Palak and Anya, you two don't have it. So I think one hack that I told you that day was using lint code. Lint code is like a Chinese copy of lead code. So you can find the same question and just type lint code over there. Like, for example, mm, so this leetcode.ca, this problem is there. 1 minute. Let me just share this problem. So this question is there. I am not sure if you can run it. Don't think that there's a provision to run it here, but at least you can see the problem. So this is the question. Okay. Um, so anyways, you can all is needed is you should know how to solve it. You really don't have to like run it for all the questions. So it's okay if you don't have the premium. Um, give me a second. Hello. Yeah, who's this? Can I talk to you in a bit? I'm right now in the session. Yeah, I'll call you back. Yeah. Um, okay. So basically, for this problem, we'll be checking if node. So over here, we can simply check if it has a successor or not. So we can first of all we can check in case if node itself is null. Uh, then we can just simply return null. This is the base case. Then we can just check if node.write is not null, and then the else part, right? So if the node.write is not null, it's pretty simple. So we can just say that node is equal to node.write, and while node.left is not null, then node is equal to node.left, and then return node. You can use a current pointer, but I just took it here itself. So uh so yeah, while so you keep on go to the right side child, and then you want to find the leftmost element in that, so you can simply return it. Please note that here we are not even looking up the values of the node, right? So although this is a BST given to us, but we really do not need the BST property here. We are not even comparing the values. We already know the in order property, so we are using that. So and this was like the question given, like could you solve it without looking up any node values, right? So here we are not looking up the node values, we are just using the property of the in order. um, Otherwise, let's say if this is the case, we don't have to write the else block, or if even if you want to write, it's completely fine. We are returning here. Otherwise, what we're gonna do is we are gonna check that the parent exists. So the node dot parent is not null. So it has a parent pointer given to us in the definition of the class. Then we're also gonna check in case the current node happens to be the right side, let's say until it is a right side child of the parent. So node dot parent is the parent, and until this node is like the right side child of the parent, it means that this parent is not the ancestor. So we can keep going up. So we can keep node is equal to node dot parent. We can keep moving up, and we will stop only at two cases. Either the parent becomes null, or we find a parent such that the current node is the left child of the parent. So in both the cases we can just simply return the parent. So even if it is null, it means that there is no ancestor, there is no in order successor for that particular node in the entire tree. And I showed you the case, right? So if it's the last node in the list, if it's the last node of the tree or in the in order list, then there will be no successor of that. So if you have to find for 3, first we'll check the right side is there, right side is not there. Then we keep going to the parent. We first go to 2, but 2 is not the answer because 3 is the right side of 2, not the left child of 2. So we go to 2. Then we further try to go up, but now the 2's parent is null. So we stop there and we simply return whatever is the parent. So null will be returned in this case. So all the cases are handled in this problem. So there are 3 cases. First is there is no in order successor found. Second is the in order successor lies in the right side tree, and the third case is like in order successor is the ancestor. And even if it's an ancestor, which ancestor is it the immediate ancestor, or is it actually happens to be like a complete chain we have to traverse, and somewhere in the chain we will find the eligible answer. uh, is this clear? Okay, and can you guys implement it as well? Please try to those of you who don't have subscription, please see if this problem is there at Geeks for Geeks, or just type in order successor in BST2 as it is. It should show up if it is there at some other place. Even if it's not, you can just simply write the code in your local in your notepad, and so that at least you have practiced it. Let me know once you guys are done with this. Are you guys done with that? Tejas is done. Palak is done. Lokesh is done. Manas is done. Anya, are you also done with this? Hello, hello. Anya, can you hear us? Okay. No worries. We'll move ahead. So the next question that we want to attempt is going to be interesting problem. So let me just first copy this into the doc. Okay. uh, so this was just copied it into the doc. Okay, the next question that we are attempting is uh, closest value. Let me copy this problem. Closest binary search tree value. So this is the question that we are practicing next. You can easily find this problem in the Geeks for Geeks also. There are two parts to this problem. This is the easier one, and this problem is a very famous problem. Like, I have seen it. If I show you the frequency of this, it's crazy number of times. Meta has asked this question 20 times in past 3 months. So this question is a very popular question, and then there is like a variation of this problem, which is a hard problem that we will do. We'll also see why that is a hard problem. So let us understand this question first. The question says that we are given a root of a binary search tree. So we are given a root and we are given a target value. Return the value in the BST that is closest to the target. So for example, in this question, we are, let's say the target is given as 3.7414. Okay, now we have to return a value which is closest to the target. 4. So 4 is the value which is closest to the target in this case. It also says that if there are more than one values which are closest, or there are two values which are equidistant, then you return the smaller one. If there are multiple answers, print the smallest one. So okay, so imagine, let's say we had to search for is there 3 already? So if we had to search for 2.5. Okay, so if we had to search for 2.5, then 2 and 3 both will be the like closest to it. Both are equidistant, but in this case we should be returning 2 because 2 is the smallest one, smaller out of it. And so I hope the question is clear to. And if we had to search for 3, for example, um, if we had to search for 3, then 3 already is present here, so we should be returning 3 directly instead of 2 or 4. So this is a pretty straightforward question. How do you guys think that we should approach it? Nobody has any inputs? Mm-hmm. 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 But how will you change your answer? Like, you will also have to. That's a right approach. But yeah, right. And if you find a smaller difference, then you will reassign the result. You'll update the result. Okay. Um. Sure. Is everyone clear? So that's a thought process. That's a right approach. But just one edge case you have missed. So if there are multiple answers, print the smallest. So we need to keep comparing that. If we have found even if we have found, let's say, a answer which is equal, in this case we should be assigning if we have found the answer which is equal, but let's say the current value, the current node that we are visiting, it is smaller than the answer that we have already set earlier. So in that case we should be reassigning or resetting our answer, the result, to the current root. Does that make sense? Okay, so let's jump directly into writing the code for it. So first what we're gonna do is we will be assigning the result. So let's say the result will be assigning to root dot value. That's the very first thing. Then I'll be saying that while root is not null, um, then so here we need to like go into the right side or the left side depending upon the direction. So we can say that if root dot val is greater than the target, in that case I will try to go into the left side. Then root is equal to root dot left, else root is equal to root dot right, because we are trying to be closer to the as closest to the target. But in this process we should also be reassigning our answers, right? So I'll be saying that if math, I'll be using an absolute function. So if mat dot absolute, if this is mat dot absolute of the current root minus the the current root minus the target that we are having, if this is lesser than the math dot absolute of the uh, so if this difference is lesser than target minus result, the result that I have. Okay, so if this is lesser than this, in that case I should be if this is the case, or there is one more case which I was talking about, so I'll be putting an or condition here. Let me just first write the conditions. So this is the first condition. If this happens, then definitely the root is the will reassign result to the root. Otherwise, or we'll also check that in case if this difference, this absolute difference of root dot val minus target, if this is actually equal to the target minus result, okay, it means that both the answers are same. It means it is a equidistant, and the so this is true, and also the root dot val happens to be the current root happens to be smaller than the result that we have captured. So in both the cases, so either this is the case or it's a second case. So in both these cases, let me just move my screen here. So in both the cases I should be, so there's a bracket here. So in both the cases I should be setting my result to the root dot value. Okay, so please make a note of the second condition as well, because we have to print the smallest one. So we will compare if the differences are same and the current root happens to be smaller than the already result that we have noted. In that case we'll be reassigning the result, and then we'll be moving our changing our route according to the we want to go to the left or to the right. This decision will be taking at the end of it. Will simply be returning the result. So is this logic clear? Everyone, is this clear? Okay, so let me run it, and we'll submit this. Okay. So now, as you can see, like this can be what's the time complexity, by the way, since we are discussing everything. So what's the time complexity? Space complexity is big of 1. We are not using recursion. We're just using a while loop and no extra space. So space is constant. And what about the time complexity? Time complexity again should be the, in the worst case, should be the height of the tree, right? Here it should be the height of the tree, um, like irrespective of because we will not stop until the root has become null, right? So we are going into the height of the tree, such that the element that such that the uh, because we are finding the target. If the target is not found, we'll keep moving towards the target as closer as possible, and until we finish the we exhaust the nodes in the depth. So it is going to be, in the worst case, the height of the tree. So let me just put this question in the doc as well. Yes, in the worst. Correct. So the in that case, the tree height itself is going to be big of n. So yeah, but you can specifically say that in the worst case, the height itself can be big of n. So that could be my, so big of n could be the worst case. Okay. Now we'll do a second part to this question, which is closest binary search tree value to. Yeah. Let me go back. In this case, no. In the average case, this again, it will not be the height of the tree. So average case is going to be, you will it will be the length of the tree, like length of the branch starting from the root node, going all the way up to the target, assuming the target exists. Uh, so if the target exists, then you will end up going to the target and probably one step further, and then you will exhaust. So if 3 had further uh, elements to it, then let's say we were finding the so if 3 had a left child to it, right? So we will stop here itself. But if 3 had right child to it, in that case, the closest value to 3 could, let's say 3.1 we are finding out. So it could be 3, or it could be the next node to 3, right? So we would be going further, but then you can say that we will go one step higher than that, and then we will exhaust it. So if I let's say we had to find if we had to find this is not a big tree, we want a little bigger tree to illustrate that logic. So if, let's say, we had to find uh, so there are some dummy nodes after 3 as well. What could be the dummy nodes? Dummy nodes could be 3.5 and 2.5, correct? 2.5 on the left and 3.5 on the right. So let's say we had to find the closest uh, value to 2.2. 2.2 is given to us as a target. Then we'll mark 4 as the answer. We'll go towards 4 is greater than 2.2, so we'll go to the left. We find 2. Now 2 is smaller than 2 is smaller than the now 2 will be the closest answer again, because so 2 will mark as a result. Then we'll go into the right side of, because 2 is lesser than 2.2, we'll go into the right side of this. Then 3 happens to come in picture. Now 3 happens to be like greater than this, and the result will not change, result will still remain 2. But 3 happens to be greater than this, so we'll try to go into the left side of 3. So essentially what we are trying to do is, the target that we have to find, we'll try to find the in order successor of that target. So 2.2 is there. We'll try to find the in order successor of that target. What's the in order successor? So if 3 has any further elements, so we'll keep on going into the deepest branch of 3. So because that will be the in order successor of that path. So if 2 point, for example, if in between 4 and 2, what will come in between 4 and 2, let's say 3.5 is there as the um, as the as the parent of 2. Okay, so 3.5 is the parent of 2 in between 2 and 4, and we had to find the closest value to 3.5. So what we'll be doing is we'll be looking to find the in order successor of 3.5. So that means that we will not we go to 3.5, and then we go to 2. We notice that 2 is because 3.5 node doesn't exist in reality over here, so that's the closest node will happen to go to. Result will still remain as 4, but from 2 we'll try to optimize it. 2 is lesser than that, so we'll keep on going to 3. So essentially we'll go to the very farthest end of the branch, but which branch will go to, um, that would be like the, in a way you can say we are trying to find the next closest element to that. So we'll happen to go to the deepest branch itself, which definitely will be the like the branch length. But will it be the entire depth of the tree? Not cannot really, not necessarily, you cannot really guarantee that. So there can be further elements to the left of 1, let's say -1, then -2, and so on. So that's the actually the depth of the tree. But do we really have to go to the depth of the tree for everything? No, not really. So yeah, it is going to be at max the depth of the tree, but it doesn't have to be the depth of the tree in the average case. So does it make sense? Okay. So now we will go to the next problem. The next problem is the closest binary search tree value to. You can easily find this problem on GFG. 1 minute, let me just share the link. Closest value to BST to G, or okay, in the, we can easily find this in solve now. 1 minute, on Code Ninjas, I think. And it are closest element, no, that's not the closest k values. Closest binary search tree value, part 2. Yeah, I think the question is here on GFG. uh, Although the approach is not really good over there, so don't read the solution. It's not solved in a optimal way on Geeks for Geeks. This is, I'll just ping the problem on the chat from, this is the algo monster, you can see. uh, okay, so this question is interesting. What this question says is that um, we are given a BST and we are given an integer k. We have to find or return the k values in the BST that are closest to the target, and you can return the answer in any order. And it is guaranteed to have only one unique set of k values in the BST that are closest to the target. Fine. So it's essentially saying that will not have more than one element. Two elements cannot be equidistant, basically. So that's fine. So let's say 3.714 is the target given to us, and we have to find the two closest values to 3.714. So the first closest value definitely is going to be 4. Then the next closest value could be 3 or 5. So but 3 is closer to 3.71. So the answer would be 4 and 3, and you can return the answer in any order. It doesn't have to be like uh, in the same order. So that is the question given to us. And Also, first of all, let me show you the stats. This problem has been asked in the 6 months by via Google and LinkedIn, Amazon. Uh, these stats are like, these are the correct stats, but these are not the only stats. So sometimes they don't update if this question has been asked by more companies, because only if people report this question has been asked to me by this company in the interview experience corner, and then they will contact and check its validity, and only then they will update. So they have a very uh, they have a certain process to update it. So this, the frequency can be much more, but yeah. And these days, one thing I can assure you is that when you go to an interview round, earlier you would mostly see the medium questions being asked by, especially by Meta, Amazon. They would never ask the hard problems. But these days, I can see in the interviews, they are asking the hard problems as well. So in one round, one problem will be medium, and second problem can be a hard problem. So don't think that you can skip the hard problems. These days companies have made their interviews really really difficult. The difficulty level has gone up by 5 notches higher than it used to be 1 year back. And complexity is from two ways. One is the kind of questions that they are asking. That's the first level of complexity. They're asking more difficult questions. And second is the kind of expectations that they have from the candidate during an interview round. Back in the days, even if you just write the code and explain it a little bit, you that would be sufficient. But nowadays they would grill you, like they would want to ensure that you are not cheating, you're not taking any help from somewhere, because it is very easy to copy the code from chat gpt, or from asking your friend to give it to you, or maybe externally taking help. But and they are filtering out all those. Even if they get a slightest of the doubts that you do not really understand what is being done, so they would evaluate you based on if you're able to do the dry run, if you're able to talk about like the minute things about this question, that can you talk about how the sequence of the nodes will be visited, or what each iteration is going to look like. If you are unable to talk about that, or if you are not very confident in discussing about that, then they they are, even if you write the entire piece of code, the most optimal solution, you're not going to get through that round. So rounds have become much complex these days. um, Anyways, so only thing that we can do from our side is to check all the boxes, and to make sure that we are like we are one level higher than what interviews are expecting us to do. So we are faster in writing the code. We are doing a deep dive on that problem. We understand everything about how the code is running, how it is working, what is actually the time complexity, is it really the height of the tree, is it, so all these minute things we are already evaluating. So just in case if any of these questions get asked, we do not like we already know how to answer them. um, Anyways, coming back to this question, so this question is a little complex in terms of the way we have to solve it. We'll discuss two solutions to this problem. One solution is going to be a easy solution, but it is going to run in a big of n time. But we have to make this work in less than big of n time. So we'll be looking at a solution which is a big of log n time, big of log n plus k. That is going to be the ultimate solution we'll be looking for. So let us let's start discussing this the solutions. First of all, before that, is everyone able to understand what we have to do? um, is everyone clear with the question itself? Okay. Cool. So the first approach that we want to do, we're gonna start with the easier approach, and which is very easy to understand. And the second solution that we will build will be on the similar lines. So what I'm going to do is, the if you understand this problem, it's a very simple problem of doing a we can solve it using a in order traversal logic. So if I, for example, showcase you here, we have to traverse. Let's say if I have a in order of this array, right? It means that this is a BST given to us. So if we create a in order is always going to be sorted, right? So we'll have 1 2 3 4 5. This is going to my in order look like 1 2 3 4 5. How much time does it take to create a in order traversal for a tree? It is going to take me big of n time, correct? So the very first idea is I'm going to create a in order and store it in a data structure. We'll talk about what kind of data structure it will be. But let's say I've created an in order of my in order traversal of my tree and stored it in a simply a in order format. Now what I'm going to do is I'm going to check the target, and I know that out of this in order sequence I just need k elements, because we need to return only the k closest values. So I can remove all the other elements one by one from this list which are not the closest ones. So the idea is that we know that in order is an increasing sequence, right? It is always like it's an ascending sequence that will be creating. So we'll be comparing this target from from the first node, from the front, and we'll also be comparing this target from the back. So basically whichever is closer, uh, just to give a perspective into that. In case if my let's say if the difference, I'm going to find the difference from the difference of this target from the very first element and the difference of this target from the last element. Assume that if this difference with respect to the first element is, if this difference is greater than the difference compared to the last element, what it means is my target is somewhere closer to the last element. Like it is not as close to the first element as much as it is closer to the last element. And since we have a property of the in order that the sequence is increasing, so it also means that as I'm going to move to the right, the target is going to become more and more closer to each of the elements that I'm encountering. So I can keep removing the elements from the first, like starting from the left hand side. So I can remove one, and then keep doing the same comparison. So the idea, just to reiterate again, will be first of all storing a in order traversal of our tree given to us. We know that in order is a sorted sequence that we have. Now we have a target given to us, right? We need to find out the k closest elements. There are two ways of doing it. Either you could also do a binary search on this, find the, let's say, find the element which is kind of closer to it, and then you can start moving in both the directions and find the k closer elements using the two pointers. That is one approach. Time complexity is not going to change a lot because already you have taken big of n time to create this in order. In the second approach, what we are doing is instead of doing a binary search, we just start comparing the first element and the last element to the target. If the last element is closer to the target compared to the first element, it means that we can start removing we can remove the first element safely. Um, and we will keep removing the elements either from the first or the last until the list, this in order list that we have, is only the number of elements in this in order list is exactly k. So, because we just want the k closest elements, so we'll keep removing the elements until we are left with the k elements out of this in order list. Is this is this logic clear what we intend to do? All right, so let's start implementing it. And also, by the way, since we have to remove the elements from either side, I cannot directly use a array list, because in array list I can only remove from the end, but I cannot remove from the first. If I have to remove from the first, then it usually takes big of n time. So I'll be using a deck. Deque is nothing but a doubly linked list. So in Python, you can just simply use I think you can simply use a list, which is a doubly linked list itself, or you can use a deck in Python as well, the deck data structure. So this is what we are going to do. So let's start writing that code. So initially, I'll be taking a deck. Uh, so dq is equal to new linked list. Then after that, I'll be calling the in order. Like I'll be having an in order routine to get the in order, and I'll be storing everything into this dq. So let me first create the in order utility over here. So void in order and tree node root. Then we'll be using a deck over here. Now in this, I'll be saying that if root is null, then simply return the standard in order stuff. So in order of root dot left comma deck. Then the next is the element we want to access and put to the deck. So I'll just say that do deck dot add. So it is going to add to the last basically. So if you're wondering where it will add to the last position. So deck dot add the root dot value, and then in order root dot write comma dq. So this is like my standard in order stuff I'll be doing. So I'll be populating this deck by using the in order traversal. And after that, once I have done that, I'll be saying that until the size of the deck is greater than k, because I want finally the k elements, right, which we need to return. So until the size of this deck is greater than k, we need to pop the elements. So either we need to remove an element from the front or from the last. So for that, what I'm going to do is I'll be saying that if the absolute, I'll be finding which element is closer. Whichever element is closer, I'll keep it, and whichever element is farther from the target, I'll remove it. So I'll be checking that. Let's say if deck dot peak first. So I'm not removing, I'm just taking a peek at it. So if deck dot if d, so I'll use a peek first method over here. If the difference from the target is this, so if this value, let's say if the difference is greater than the last, okay, so what it means that the last element here is closer to the target than the very first element. In this case, we're gonna be removing the very first element itself. So I'm gonna say pole first, okay, else we can just say pole last, and that's it. So essentially we have first done a in order traversal, stored that results into a doubly ended queue so that we can remove it from both the ends. And we'll keep removing the elements from either of the end. Whichever end is the whichever difference is more, we'll remove that one, and then keep the other one, and we'll keep on doing it until the queue size becomes equal to k. So at the end of the while loop, the number of elements in the queue will be k itself. So now I can just simply return, since I need to return it in a form of a list instead of a deck. So what I'll be doing is I'll create a array list from the deck. So and then just simply return it. That's I can just need to pass in the data type as well. So that's all. uh, is this logic clear to all? This is the very first, this is a very simple logic but a very effective solution, and simplicity at its best. But yeah, the time complexity we have to optimize a bit more. But yeah, this can be the optimal solution if the tree is not. So in the follow-up, they're asking if the bst is balanced, uh, could you solve it in a less than a big of n time. So it means that we want to solve it in the big O of log n time. Essentially, this is what it means. Anything less than n is like log n, right? Especially in the tree context. So if it's a balanced tree, this solution is still going to take me big O of n time, even if it's a balanced tree. So let's run it first. 1 minute. So I think the spelling mistake, DQ. Okay, so this this works. Let's name this solution as the first solution, okay, that we have done. Now we'll be taking a look at the second solution, which is going to be an interesting one. So let's talk about the second one first. um so if you try to take a look at this entire thing, right, what we are basically doing is, what we had to basically do, if there was a way we could get closer to this target. Let's say if we could get closer to this value, this target value, for example 3, and then uh, let me tell you my perspective. For example, this is my in order, right? 1 2 3 4 5 6 7 8 9. Assume that this is my in order traversal for a tree. Now I have to find the target that is given to me is, for example, 4.2. 4.2 is the target given to me. So, and the value of k is maybe 5, right? Now idea is that I have to find the 5, or maybe the value of 5, k is, let's say, 2. I have to find the two closest elements to 4.2. So essentially one will be 4 and second will be 5, right? And if I had to find three elements, then we would have to see which one those three are. If let's say if I had created a successor list and a predecessor list with me, and I'm not saying to create to have all the successor list, but we'll do a lazy creation. So assume that if we have a successor of 4 with me, successor of 4.2 with me, so 4.2 does not exist here, but what are the remaining ones that exist starting from 5? So if I store all the successors with me, maybe 5 6 7 8 9, for now just think of it like this, but we'll not be storing all of them. That's where the optimization comes into picture. And if I also store the predecessors list with me, what are the predecessors of 4.2? 1 2 3 4. So these are the successors and these are the predecessors. Isn't it really easy to find out the closest k elements from here? Like I can basically first compare the very first elements from each of the list. So compare each of the list means like the last element of the predecessor and the first element of the successor. So we can compare 4 with 5, uh, whichever is smaller, you just return it and you can remove it from the predecessor list. So let's say 4 is the nearest one, so we can remove 4 from the predecessor, and we add 4 to the result. Now it will become 3. 3 is the nearest predecessor and the next successor is 5. So we can simply compare 3 and 5 with the 4.2, whichever is nearer to 4.2. So 5 is nearer to 4.2. I can remove 5 from the successor list and I can add it to the result. And then the next successor I have is 6. The next predecessor I have is 3. So then again I can compare which element is closer to 4.2, and I can simply return that, and we can keep doing it until the k is exhausted. Is the logic clear? Right. After this I'll discuss about a little more optimization about the successor and predecessor, but is this logic clear what we are intending to do? So we are not looking to find out the entire in order. We don't care about the entire in order. We just care about the in order successor and in order predecessor, which are starting from this target itself. Now coming on to the, just give me one second. हाँ यहाँ लगा दे भाई म्यूट. एक सेकंड म्यूट नहीं है. ठंडक से कर दूं वहां लगा दे इसमें ब्लोअर नहीं है थोड़ा पास बैठी उसके बाद अच्छा थोड़ी देर चला दे बस 5 मिनट okay. So the idea about in-order successor and predecessor is दोनों रोड पे चला दी let me talk about from the given example. So what we'll be doing is you saw our example of doing a DFS traversal using stack, right? In the stack, when if you remember the in-order traversal, what we were doing was we were storing the in-order successors in the stack. Um, or you can say we were actually storing the in-order successors in the stack, but not all the elements we were storing. We were only storing till the height of the tree. थोड़ा पीछे कर दे इसे. So we were only storing till the height of the tree. So uh, just to give you a reference, for example, if we were using the stack, if you remember the approach, we started from so imagine that we are doing a DFS in order traversal, uh, and we are doing it iteratively, so using a stack. So initially the stack is empty, then we add 4 to the stack, which is the root node, and then we keep adding the elements to the stack. So 2 will come at the top. We'll keep on going to the left until the left branch is exhausted, and then we keep on adding 1 again, and then it will get exhausted. So if you have to do a next operation, so you saw that example in the BST iterator question also, right? So if you have to do a next, the next can be recovered from the stack. And what is the meaning of next here? This next is nothing but the in order successor. So what is the next element? 1 is the next element. So we can pop 1 from the stack. So if I rename this stack, I can also rename this stack as a in order successor. In order successor stack. If you notice, I'm not saving all the elements into the stack right away. I'm not saving all the in order successor complete list. I'm only storing the elements which are required to help me find out the next successor, and I'm making sure that this can be done in a log of h, uh, the log of n space, where log of n is nothing but the height of a balanced tree. So if it's a balanced BST, then the height is going to be log of n. So the number of elements that will go into my stack is going to be log of n. So the first element, the successor is 1, the next successor is going to be 2. But when we so initially we'll pop 1 from here, but and then we pop 2. But when we pop 2, we'll see if 2 has any right side branch. 2 has a right side branch, so we'll push 3 again here. Okay, and so on. So the next successor is 3, then we'll remove 3, then next successor is 4, we'll remove 4, but after removing 4 we'll add 5. I hope this part is clear to everyone. So we are going to maintain two stacks. One is for the in order successors, and the second stack we are going to maintain is for in order predecessors. So we are not maintaining the entire list, we are just maintaining the stacks to optimize on the time and space both. Is that piece clear? Okay. um Also, one small optimization we do not need all the in order successors. Like for example, the case that I told you, 4 to 1, this is when I have to find out, let's say, all the this is the in order successor list or in order successor stack for the entire tree. But I'm not interested in knowing about the entire tree. What I'm interested in knowing is that I'm only interested in knowing the in order successors of the target. So if the target is 4.2, let's say in this given example number 1, the target is given as 2.5, for example. So I don't want to save 2 as part of my in order successor stack, because 2 can never be the in order successor. So it is always going to be like 3 is going to be my in order successor, you can say that. Does it make sense? So I don't want to store all the elements into it. I just want to store the elements which are actually greater than the target node that I'm having, and I'm going to start from there. I hope that makes sense. 1 second. For 4.2, what is the in order successor and what's not? So I was taking an example of 2.4, for example. Let's say target is given as 2.4. Then for 2.4, 2 can never be an in order successor of 2, right? In order successor of 2.2 can be 3, it can be 4, it can be 5, but it can never be 1 and 2. So in my in order successor stack, I will never be pushing the elements which are smaller than the target that I am looking for. So what it means is that when I'm computing this in order successor stack, I'll be saving on the time, and I'll not be pushing any elements into the stack which are lesser than the given target. Same thing when I'm computing the in order predecessor stack. So when I'm computing this in order predecessor stack, here I'm going to push all the elements, um, and again, I'm not pushing all the elements, I'm just pushing the elements which come which are falling into the height of that. So when I'm going into the depth of the tree starting from the root node, all the elements which fall onto that branch, and also making sure that the elements that I'm pushing, they are either greater than the target in case of successor, and they are smaller than the target in case of predecessor, so that I'm only pushing the useful elements which are useful to me in that uh, for that piece of logic. Does that make sense? Okay, and the logic we have already talked about, right? So we compute the in order successor list. We so you can for the logic understanding part, you can take this example, the successor list and the predecessor list, and using that list we'll be finding the top of the predecessor. So assume that if it was a stack, if it was a stack, then so for example, uh, so let's say 2.2 is the target. Okay, this is the target that we want to find. So I'm not going to be making this list like this, and I'm going to be making a stack. In this stack, how we are going to do is, we are we are going to start from the root, and we are going to check if the root itself is e- if the root itself is equal to the target. It means that we have found the closest value, the root itself. So in that particular case, like, that will be one condition, and we'll break over there, we'll just add it uh, to the target list, and then we'll break from there. But otherwise, what we're going to do is, so initially we'll be starting from 4. 4 is bigger than 2.2, correct? So I'm going to add it to the stack. That's the very first thing. And since I have added it to the stack, I know that I need to go to the left part, because I'm creating the successors from the right side of 4. We can easily access from 4 itself, but we we are trying to generate all the successor stack links. So I'm going to go to the left of 4. The next element I find is 2. 2 is smaller than my target, so I'm not going to add 2 into the stack. In the previous case, we would add 2 to the stack as well, right, when we are just doing a generic DFS uh, iterative approach. But here we are not going to add 2 into the stack because it is useless. Here I'm computing the successors, it has to be bigger than that. So then I'm going to go to the right. On the right hand side, I see 3, so I'm going to add 3 into the stack. So the element at the top of the stack is going to be 3. Then I'm gonna create a predecessor stack, which is going to look like, so for the predecessor stack, will be starting from the root. Now if root is lesser than the target, I'll add the root, but 4 is not less than 2.2. So in that case, um, I cannot add it. I'm not going to add it uh, to the stack. So I'm gonna go to the left part because it is anyways greater than that. So we will come to 2. Now 2 is smaller than the uh, 2 is smaller than the target. So I'm gonna add 2 uh, into the stack. Since 2 is actually smaller than the target, I'm gonna go to the right. Now we reach to the 3. 3 is greater than the target, so I'm not going to add it to the stack. Then I'm going to go to the left, and we will reach a null, so we'll stop there. So the predecessor stack is going to contain 2 and the successor stack is going to contain 4 and 3. Now let's see what will happen. The next thing, that we are going to check is, uh, I'm going to check the top of my, like I'm gonna peek over the element. So 3 is the element which is the successor, and 2 is the element which is the predecessor. This is also true. So if you take a look at, let me just remove this entire thing. If I just create an in order traversal for this tree, it is going to look like 1 2 3 4 and 5, right? And 2.2 ideally comes somewhere in between this, correct? So if I show you the, so 2 is actually the closest predecessor to 2.2, and 3 is the closest successor to 2.2, and that's what our stack shows. In the stack, the top of the stack is 3, and then the top of the stack, the predecessor stack, is 2. So what I'm going to do is I'm going to peek take both these elements and compare the difference with the 2.2. Whichever is nearer, I'll pop it from the stack. So here 2 is nearer to 2.2, so I'm gonna pop 2 from the stack, print it into the result. So result is 2. But when I pop 2 from the predecessor stack, I'm gonna check, does it have any left children or not. Remember, it's a predecessor stack, not a successor stack. In the successor stack, when we pop an element, we check if does it have any right side branch or not. If it has any right side branch, we add that branch along with all its left side links to the successor stack. But in case of predecessor stack, we're going to do the opposite. So we popped off 2 from the predecessor stack. Then we're going to check, after like popping this, does it have any left branch, and does it has any left child, and that child has any right side branch or not. It has a left child 1, so I'm going to add 1 to the stack, and then I'm going to add all its right side children, like all its right side branch, into the stack. It does not have any right side branch, so 1 is enough over here. uh, in the next step, so 2 is already our answer, that is the one closest answer that we have gotten so far. And let's say we had to find out k is equal to 3, we had to find out total 3 numbers closest to 2.2. The next thing, we are going to compare 3 and 1. So 3 minus 2.2 and 1 minus 2.2, so whichever is nearer. The nearer is 3, so I'm going to remove 3 from the successor stack. Before removing 3, I'm going to check if 3 has any right side branch. 3 does not have any right side branch, so we don't add anything back to the stack. So we print 3 into the result, and the stack becomes, as of now, 4 and 1. Then we're gonna, still we have to find one more element. So I'll be checking the distance of 1 and 4 from the target. So 4 minus 2.2 and 1 minus 2.2. Definitely 1 is the closer one, right? So I'm gonna be removing 1 from the stack, and I'm gonna push 1 into the result. And after removing 1 from the stack, we'll be checking, does 1 has any left branch. 1 doesn't have any left branch, so nothing, we won't be adding anything back to the predecessor stack. What it means is that we have exhausted the predecessors, there is no predecessors left. And this is also true if you look at the in order sequence. There are only two predecessors of 2.2, I mean, assuming that 2.2 was a given valid element, then there were only two predecessors, 1 and 2, and both of them we have added to the result, and that's why our predecessor stack is empty. But the successor stack is still containing 4, because 3 is already added to the result, so 4 is there. We have not added 5, because 5 we will be adding using 4 itself. When we pop out 4, then we will add the right side child of 4 into the successor stack. So assuming if k was 4, then we would be, then predecessor stack is empty, so we'll be removing the element 4 from here and adding it to the result. And when we remove 4 from here, we will check does it has any right side branch, and so we'll be adding the right side branch, and then all its left side branching elements. But 5 doesn't have any left side, so it will remain like this. Is this part clear, the approach that we have discussed for this? Someone who is not clear with this approach? And can someone explain me why this takes log of n time and this is not O of n? For a balanced, if a tree is guaranteed to be a balanced BST, let's say the follow-up question that is being asked, assuming that the tree is a balanced BST, can you tell me that why this I'm telling you that the time complexity is log of n. I have also told you the approach, the entire approach. We have also done a bit of a dry run using an example. Can you guys tell me why this approach is log of n, the time complexity? See, I'll tell you one thing. If you guys don't interact much, like for me, it is not going to affect me anything. For me, someone who the more interactive you are, you can think of it like I'm giving a more of a mock interview kind of a setup also, because these questions will be asked by your interviewers. If you remain silent all the time, it's okay, I can just do a one way communication and I'll wrap up the session, I'll go away, not an issue. But don't complain to me at the end of the 3 months that, hey Mohit, I'm giving interviews but I'm not still, like something is missing, I'm not able to speak up things. So if you do not speak up, if you remain shy, feel free to be that way, not an issue. But if you really want to utilize these sessions, because here I'm trying to add value to you, that's what the intent is. So if you don't want to be interactive, you are the one who is losing out here. Nothing happen. There's nothing that is going. I'm doing my job here, but it's up to you how much value you want to gain out of it. Yes, Manasvi, go ahead. Right. Mm-hmm. Are you talking about the time complexity or the space complexity? Okay. So time complexity, it so basically for the time complexity part, we have to fill in the successor stack once, right? And when we have the way we are filling the successor stack is we are taking all the branch elements, like which fall into that branch. Let's say the deepest branch starting from that node, the starting from the target node or the one that is closest to the target, and then going filling all the values in one branch until the height of the tree is covered. Similarly, we are going in the opposite direction for the predecessor stack. So essentially, the height of the tree is going to be, we have to iterate over twice the tree, like two times, one to fill in the successor stack and second to initialize our predecessor stack. So it is going to take us log of n, twice of log of n, or which is essentially log of n itself, to create the stacks itself. Once we have done that, we will be visiting, like we'll be pulling out each item from the stacks, and then we'll be doing it k times the iteration, right? So log of n initially to generate the stacks, then k iterations we are doing. For every iteration we'll be pulling an element from the stack, and then in this process it may happen that for some of the elements we may need to push the, let's say, the, if there's a right side branch for the successor stack, we need to push the right side branching root, and then the all the left side elements to it. But that would be done as a one time thing, not for all the k iterations. So for one of the things it can be like log of n is again added to it, to the time complexity, but it is not going to become k times log of n. So the total time complexity is going to be log of n plus k iterations to pull k elements from these two stacks. Does that make sense? So initially we have to initialize the two stacks, right? To initialize these two stacks, it is going to take us log of n time, because we have to iterate till the height of the tree in the worst case, right? For filling these two stacks. So that is the first aspect. So log of n to initialize the two stacks. Then the second thing, we will be, we have to fetch the k values. So we'll be using a while loop to, like, fetch the k values, and then we'll be picking the top of the stack, top of the items from both the stacks, and comparing it against a target, whichever is closer. So in that way we'll be popping the stacks, and we'll be doing it total k times. So, and the average time complexity to pop the stack is big of 1. That's the, like, amortized or the average complexity, not the worst case, but since we are doing it k times, so average is big of 1, so it becomes big of k times. So overall time complexity will be height of the tree, a log of n plus k. And if k is very small compared to n, then we can, like, ignore k, and we can just say log of n is the overall time complexity, right? Right. Yeah, right. And what could be the space complexity in this? We are using space, right? We are using these two stacks to store things. Correct. Yes, that's right. So log n is the space complexity, and log n is again the time complexity as well. Log n plus k is the time complexity for this. So, uh, is this clear, the solution to everyone? We did the dry run also, we explained the solution also in depth, and also discussed about the time and space complexity for the optimized solution. So we're going to implement the second solution. We're going to do it, the solution, the implementation is going to be the straightforward easiest implementation. So we're going to break it down into the functions, just to make sure that the logic remains simple, easy to remember, easy to write, and easy to replicate next time when you're doing it. So we're gonna do it in that way. I'm gonna create a two over here, okay, and then to, so the very first thing that I'll be will be doing over here is, we will be taking, where is it? So we need to return this list of integer. So I'll just let me switch to the bigger screen. Okay, so first I'll be taking the result as the, so this is the final result that we need to return. Then I need to initialize the the successor stack. So I'm just gonna call it successor. Then we need to initialize the predecessor stack. I'll just call it pre. Okay, uh, maybe predecessor and successor. Okay, then I need to initialize both these stacks. So what I can do is either you can write a helper function to do that, or you can do it within the same code. If you, so I'm gonna create initialize successor. So I'm just gonna write a helper function to do for both. So stack integer. I need to pass the tree node root, and also we need the target as well, because we discussed that we don't want to put everything inside these. Since it's a successor to, we are filling the successor stack for the target, so the values that go inside the successor stack have to be greater than the target. It greater than or equal to the it can also happen, by the way, one edge case can also happen. Just to give a little, one edge case can be there that if the target itself is present in the tree, so instead of 3.7, let's say it is a the value is 2. Now the question is that one, when we are creating these two stacks and we are fetching all the values from there, so one of the stacks should contain the should contain this target. Let's say if the target is 3, then if the target was 2, then 2 is actually present in the stack. So the logic that we are writing, what would happen is if both the stacks might contain 2, but we need to print 2 just once. So we'll have to like remove 2 in that case. So just to give an example, if we are finding out the predecessors, right? So predecessors of 2, let's say predecessors of 2 is going to look like, um, it can look like, we are having um, we are having two only, because as soon as we find the closest value, um, we kind of, if it's an exact match, then we'll just stop, because one we can easily find from 2. when we pop when we pop 2, then we'll go to the left and we'll add it to the stack. And the successor of 2, if we are looking for the successor of 2, then we'll add 4 into the stack first. Then since 4 is greater, then we go to the left. Now 2 is actually the exact 2 is actually the exact match. So I'm going to add 2 also into the stack. But at this point I'll not add 3 into the stack, because 3 can be easily derived from 2. So when I pop 2 from the stack, then all the right side child and all its left branch I'll be adding into the successor stack as per our usual algorithm. So I'm going to add 2. But if you notice, 2 is there uh, in both the stacks, right? It is there in the predecessor also, and it is there in the successor also. So in this case I should consider it only once, isn't it? Like, otherwise, if I have to, if the value of k is 2, if I had to find two elements, then what would happen is, and the target is 2 itself, then I would end up, the result will end up 2 comma 2, which is not right. 2 is just present once inside the tree. So I have to just handle this case, and this case can be easily handled by checking the top of the stack. If the top of the stack is same in both the stacks, then I can just remove this value from any one of the stacks. And so I can remove it from successors, for example, and now the rest of the algorithm remains same. So this is the only the corner case that we need to handle in case target itself is present in the tree. So yeah, so in case if target is not some random value, but it is actual value present inside the tree. Does that make sense? Okay. um cool. So having said that, we'll be writing. So first we created the resultant list, then we created the successor stack, then the predecessor stack, and then we're gonna initialize the successor stack. That's the very first thing we'll be doing. To initialize the successor stack, I'll be saying that while root is not equal to null. um, okay, in case the root dot value, this is the very first thing that I was talking about. If this itself is present in the tree, then I'm going to add it to my successor stack, successor dot push root, and then I can just simply break from here. I don't need to add further values, because if it's a successor stack, then all the values higher than the root will be towards the right of the root, and those I can simply get it once I pop root. I'll be adding the right child to the stack again, so I don't need to do anything further. But in case, else if, we can say that if root dot value, let me just put it here, if root dot value is actually, let's say, greater than target, in this case, root dot value is greater than the target, it means this can be a potential successor. So I need to add it to my successor list. So successor dot push root, and now we can go. Now I know that since I have added the root, all the right subtree of root will be handled by the root itself, because once I pop the root, then I'll add back the right subtree elements. So I just need to go to the left here. So root will be root dot left, and else root is equal to root dot right. Okay. um, so this is the same concept as we were doing the DFS in order traversal using the stack. So successor is simply a copy of that. Only thing that is newly added is this part. If it is equal to the target, then just simply do it. And if it is not less, and if it is greater than the target, then keep pushing it to the stack. But if it is not greater than target, if it is less than target, then don't push it to the stack. So we don't push it back to the stack in that case. So this is the initialization logic for my successor stack. I'm going to have the similar logic for the predecessor. So I'm going to copy this entire thing to the, I'll just create another function with the same name. Let me make it, so here we'll just say that predecessor. Okay. We'll pass over here a predecessor stack, and instead of successor, predecessor. So here what we need to change is, if root dot val is equal to target, same logic, just push it to the predecessor stack and just break it over there. Then else if root dot value is greater than the target, so in this case, if it is less than the target, then we need to do this. We need to uh, push this value to the stack, and then go to the right. Okay, because the left ones will already be handled by this root that is being pushed. So now go to the right subtree and check if there are any predecessors, and otherwise go to the left. So that's the only thing. So this is the very first, this is the initialization of both the stacks. Now, so I'll be first calling this initialized successor. So I'll be passing root target, and then I'll be calling the initialized predecessor. Same thing I'll be doing, passing root and target. These are the two things. Then after doing these two steps, I'll be checking the corner case. Corner case, if target is present in the tree. You can also avoid this corner case um, by not pushing one of them into the uh, stack itself. So you can break as soon as you find a target, but don't, um, we need to push. Actually, we cannot avoid pushing. mm, Give me a second to think about it. We need to push, actually. We cannot avoid pushing. The reason for that is, um, if we don't push, whatever is the remaining, let's say, as soon as we find the target, we are finding the successor of 2, so we are creating the successor stack. If we don't push 2, then we'll not be able to, because we break over there, then we'll not be able to get to 3, right? 3 is, 3 is also a successor of 2, correct? So we have to create an entry, and same thing goes for the predecessor as well, so we cannot escape that. But we'll be handling it once we in once we see that both the values of the stack, the top of the stacks, are same. So if target is present in the tree, in this case, so corner cases, if the target is present in the tree, in this case, top of both stacks are same as target. Okay, so this is guaranteed to be there if this happens, and then we have to remove one of them. So what we'll be doing is, I'll be saying that if, let's say, my so I'll be basically checking if successor dot peak, if this is same as predecessor dot peak. Okay. um, and both the, so if both the values are same, so since these by the way, these are the tree nodes, not the integers. So I'll be just changing it to the tree nodes. And one second. Yeah. S- um okay, so these are the tree nodes, and in case if the peak dot val, we need to say, um, so if both the values are same, it means that they are referring to the value present in the it means that the target is actually present in the tree. That's why the top of both the stacks are same. And also, before checking it, we also need to do a check that if the stack is not empty. So this is just to make sure that we are not invoking this function on an empty stack, and predecessor is not empty. Can there be a case when any of the stack is empty? Guys, can there be a case when any of the stack is empty? There can be, right? So let's say the target is 5.5. In that case, there is no successor. The successor stack will be empty in that case, right? So will not be, so we have to make this check before. These are just the corner cases. In case of any of the stacks is empty, then only we both the stacks are not empty, only then we make this check. Okay, so if this is there, then we basically, what we are saying is that we pop an element from the predecessor, and basically we we pop this element from the predecessor and get to the next elements. So for that, we have to, just like this, we have written the helper method. So I'm going to write a method to pop an element uh, from the successor stack, and also from the predecessor stack. So I'll say that pop, um, and this is going to return me as well. So I'll return an integer. So pop an element from successor, or you can say pop from successor. Okay. So you can also say get next successor, whichever you want. So here I'll be passing the tree node. I'll be passing the stack. um, so here we'll be passing the successor stack along, and in this successor stack, what we'll be saying is that tree node, let's say the result is going to be successor dot peak, for example. We can simply pop it, actually we don't need to just peak. And now we have to see if this result actually has a right child, then we need to add that right child and all its left branch to the back to the stack. So I'm just gonna say that current is equal to result dot write, and while current is not equal to null, then successor dot push current, and current is equal to current dot left. This is pretty standard. This is a pretty standard stuff that we were doing for the in order, for our in order. And here I'm gonna return the result dot val. Okay, so uh, so this one I'm gonna return. Similarly, we'll just copy this method and create another method for pop from predecessor. So in that case, I'm gonna be using a predecessor stack instead of successor stack. Okay, here we'll be popping from the predecessor, and now we have to go to the left. We have to just do the opposite, right? And in case if current is not null, then we push the current into the predecessor, and then current is equal to current dot write, and then just return the result. Okay, so this is my popping from the predecessor, correct? um, so ideally what we are going to do is, in case if both the values, if the top of both the stacks are same, we can pop from any one of them. We don't want, so we can say that pop from the successor, for example. Okay, since both the values are same, so just remove one of the values, and when you remove it, it will add back all the, let's say if it has a right side branch, it will add back to the stack, that thing. So this is to handle the edge case. And now we can just simply, the rest of the logic is pretty simple. We have like while k is greater than 0. Okay, so until this is there, then we'll be popping an element from either of the stack, whichever is closer. So that operation we just need to do. There are a couple of corner cases again. Before popping, we can simply check if either of the stack is empty. So if, let's say if successor stack is empty, okay, in case if this is empty, then we don't have anything to compare from successor. So in that case, I can just simply add to the result. We can just simply pop from the predecessor. So I can just simply say result. We have already have a result here, so result dot add. I can call here pop from predecessor, and I can pass here predecessor stack. And or maybe we can do it into, so I can just get a tree node here. uh, so node is equal to this, and then result dot add node dot val. Okay, this is the case in case successor is empty, so we don't have to compare anything. It means the closest element will be the one from the predecessor. The second thing we can check is, in case if our predecessor is empty, so same thing we can do over there. We can just pop from the successor in that case, and append it to the result. Okay, the last case will be when neither of them is empty, so both of them uh, has the leftover elements remaining. In that case, I need to check the difference. So first we can, and this difference is a form of a floating value because the target is given as a double. So what I'm going to do is I'm going to create a double, let's say the successor difference. Okay, I can say that over here, I'm gonna find the difference with respect to the given target from the successor peak. So I can say successor dot peak dot val. Successor dot peak is going to give me a tree node, so I'm gonna use a dot val over here, minus target. So this is the very first value that we are basically getting. uh, in fact, we can just do it in a single thing. So we can say that if successor dot peak dot value minus target is greater than predecessor dot peak dot value minus target, and I need to use absolute here since um, we want to find the closest in any direction. So I'm going to use a absolute function here. So let's say this is the case. Okay, so if mat dot absolute, one second, minus target, if this is greater than math dot absolute predecessor dot peak dot val minus target. Okay, so if this is greater than this, let me just make it here so it come in a single line. So if this is the case, okay, it means that the closer one is the predecessor, right? So closest one is the predecessor. So in this particular case, I'm gonna go ahead with my predecessor. So I'll say that uh, tree node is equal to predecessor dot pop from predecessor and pass over here predecessor and add the result in the node dot value. Okay, else will be popping from the uh, else will be popping from the successor, pass in here the successor um, stack and just add the value to over here, and then finally just return it. So that is the whole thing. So yeah, this is a hard problem, like in terms of the edge cases that you need to handle and also think about the time complexity. And so yeah, if you want to do if interviewer asks you to do it with this approach of login, then yeah, this problem becomes hard. Is And also we need to subtract k. So either I think I just write k over here so I can do a k minus minus at the end. So we're gonna pop an element from both the stacks until we have exhausted all the k's. So um, is this logic clear to everyone? Okay. um Sure. So let's try to run it. This is going to be our solution 2. So what we're going to do is I'll copy it and we're going to uh, call this method over here, return, pass here root target. Okay. Let's see if this runs. Definitely there will be a lot of compilation errors initially. Math dot absolute, I think some brackets we might have, yeah. So math dot absolute, uh this should be this. Sure. Okay. uh Fine. So this is the first error that we had, and then line number 44. uh I think it should work now. Let's try to see it. Line number 41, math dot absolute minus target. Okay, so this closing bracket we had missed. Initialized, initialize successor, root target, and okay, so three parameters we needed to pass: root, target, and the name of the stack. So root target comma successor and root target comma predecessor. So these are the three things we needed to pass. Pop from predecessor. The pop from predecessor is directly giving me the int value actually, so uh, I don't need to typecast it there. So what we can just do is we can use call it directly inside the result dot add. I'm gonna remove it, make it simpler. So pop from here and same thing goes there as well. So I'm gonna be updating it here directly. Remove it. Okay. Um. Okay. Same thing here. from predecessor, and again same thing here. Then I can remove this line, can remove this line. Okay, so um fine, let's try to run it now. Okay, so this works, and we submit it, so this should handle the cases. Is this clear what we discussed? If is there any confusion in this question? I hope it should be clear. We discussed in quite a lot of detail. I'm going to copy this entire thing. It has, we discussed both the approaches to solving it. I'll paste it in the doc that we have. So give me a second. Yeah, I just pasted it in the doc as well, so you guys will be able to see it in the doc. uh, okay, cool. uh Fine. I think we are pretty much done. One more question. I don't know if I'll have time for it, but I'll just discuss it briefly, and probably I would want you guys to give it a try. The question that I would want you guys to give it a try is, uh, let me diameter of a binary tree. I think everyone would have seen this problem earlier, right? Maybe some time back. If not, it's okay. It's not an easy problem, by the way. It's written as easy, but it's a medium problem. It's wrongly categorized as easy. So diameter of a binary tree basically means that you can start from any node, like from a leaf node. So what's the longest path that you can have between two nodes in the tree? That is called the diameter. So the diameter is the length of the longest path between any two nodes in the tree, and this path may or may not have to pass through the root. It may not have to pass through the root, not necessarily. Um, and and the length of the path is represented by the number of edges between them. So here the longest path is, one path is 4 to 5, but is this longest? This is total, there are like total 3 nodes are there in this path, right? Or 2 edges. The second path you can have 4 to 1 3. So here this path is the longer one, 4 to 1 3. So the answer should be 4 to 1 3, and then the second path can be there, which is 5 to 1 3. Both are of equal lengths. So the diameter is going to be like, the diameter you can say is that 4 to is the 4 itself. The diameter length is number of nodes minus 1, basically, which is number of edges. So this question is a very very popular question. You can see it asked in every single company. Like, I don't think that this question has been skipped anytime. It has been asked every single time, this problem. So and this problem is a very easy problem to solve, but it's once you understand the concept. So what do you guys think, how we can solve this problem, the diameter of a binary tree? Any thoughts? Find the maximum of the subtree length. Yes. So basically you will find the maximum length of the left subtree, maximum length of the right subtree. You add both of them and add 1 to it. So 1 plus maximum length of your left subtree plus maximum length of your right subtree. Does that does that make sense? So ideally, and using this problem, you can solve multiple problems like this. I think an array tree, we can leave it for now. We have not gone into an array trees. And the second problem is not a tree problem. It's a string problem. So we should be, but it's fine. So let me just solve it. We are a little less over time. So basically, the idea is simple, that we want to find out um, the idea is pretty simple. We want to find out the length of the longest branch in the left, then the length of the longest branch in the right, and then we add both of it and plus one to it. But it may possibly happen that the new node that you happen to go into, it will give you the localized maximum diameter. Like for example, the localized maximum diameter of a subtree rooted at 2 is 3, right? Because 1 is the branch here, or you can say 1 plus 1 2, whatever. So the maximum diameter is 2 for subtree starting at 2. But for the subtree starting at 1, the maximum diameter is like, there are 4 nodes can be part of it, right? So what is going to happen is, from every node is going to return the maximum length from one side. So for example, 2 is going to return um, the maximum. So what we are returning the maximum of the path. So the maximum path starting at 2 can be the left path or the right path. So the maximum path length is 1. In both the cases, it is going to return 1 to the root node. So when 1 is looking at it, it is going to return 1 to it. Then 1, it is going to go to the right side and going to check like what's your maximum 1. So 3 is going to say that, hey, my like my maximum, and it is going to return 1 plus of that. So two's maximum is 1, but then there is one more chain here, so it is going to return total 2 to the root. And then the same thing, 1 is going to recursively invoke it for the right subtree. For the right subtree, for the node number 3, we are going to ask the same question. So 3 says that I don't have any further children, so it will be returning, so the left height and the right height both are 0 0. So the max is 0, and it is going to return plus 1 to that. So it is going to simply return 1. So 1 is going to say that, oh, I am getting 2 from here, 1 from here. So total answer is going to be 3 for me. That's what is the total diameter. So this is the entire concept. So if we start writing it, it probably would make much more sense. So we're going to say that if uh, so what we're gonna do over here is, two things every node is going to return. So a node is going to return the longest path that it has, whether it has the left longest or the right longest. Whichever is the longest one, the length of that longest path, it is going to return to the upper one. And the upper and the root, let's say the parent node is going to make a decision, is going to compute the diameter. So every parent node is going to compute the diameter based on the information received from the child node, but it is not going to return back the diameter itself. So diameter itself is not returned back, but what is returned back is the length of the longest chain, either on the left side of the tree or the right side of the children. So we need to compute diameter externally to it. So what I'm going to do is, I'm going to create a, let's say, a diameter. um, I'm going to create over here. We can look at, without using any global variables, how we can do it. It's also pretty easy. But right now I'm going to solve it using that, and that can be one homework for you guys, how to do it without using uh, the the global variables. So here, I'm going to call the longest path. As I said, every this method is going to return me the longest path, and within that it is going to compute the diameter as well, and then I'm going to return the diameter. Now in this method that we are gonna write, so over here I will be writing int longest path. One second. int longest path, and then I'm gonna be passing tree node root. Over here we'll be saying that if this root is null, then we can simply return 0. There is no longest path here. Then I'm gonna compute the left path, that let's say the left path and the right path. So longest path root dot left and right path, let me just write the full thing. Right path is going to be same as our longest path to the right. Okay, so once we are done with this, now we are going to count the diameter. So diameter computation is going to be happening uh, based on the result that we have got from the left subtree and the right subtree. So for the diameter, I definitely want to be maintaining the max of it. So I'll be checking if this is max of the existing one that we have already gotten so far, or I'm going to be computing the new diameter. So please note that the new diameter is going to be the length of your longest path that you're getting from both the things. I'm not going to add one to it because the diameter is one less than that. So if you notice the diameter in this case, the diameter is not 4, the diameter is 3, so it is the number of edges. So that's why I'm not adding plus 1 here. But when I'm computing the longest path, I'm going to be adding the total number of nodes that come into that particular path. So I'll be returning the longest path as I said in this function, and diameter I'm going to be computing and setting it every single time I'm doing it. So here I'm going to say that whichever is max, left path or the right path, so you pick the maximum value out of it and add 1 to it. So 1 plus this, so we'll be returning this as the um, so this is going to be returned as the longest path that we have. So why we are adding 1 here? Because the current node also contributes to the path itself. So whatever path is coming, whatever value is coming from its children from the left to right, pick the longest one and then append the current node to the longest path. So 1 plus the chain that is coming from the children, and you return the longest path in your and whenever you're calling, the parent will be getting the left path and the right path, and the diameter you're computing based on that. So you're just adding the left and the right, because diameter is what you add the left path and the right path, and definitely you're not considering the nodes, you're just considering the edges. That's why you're not adding plus 1 here. So it is like plain simple. Is this logic clear, what we are doing, how we are computing the diameter? Okay. um and that's it, like, and then we can just simply run this. We can just simply run this and see. We missed 1 second. Oh, it's an assignment. Int longest path, tree node, tree. Okay, there's a typo. Okay, so this works, and we can submit it. So this question is also done. I'll just paste this question into the doc. uh, so you guys can practice. I think there's a lot of questions to be practiced now for this week. We have done close to, I think, 17-18 questions. So uh, let me mm, just add everything into the doc. So yeah, it's added to the doc now. uh, what is remaining in this whole thing If I show you, I think if you check the WhatsApp chat, I just pasted the list of questions that we had. So some questions I would like you guys to give it a try. I don't want to discuss every single question in the session, otherwise we'll not be able to progress a lot. So validate BST is a simple question. You can try this. Probably I can discuss it in the session also, but this question you can give it a try. The next question is also pretty simple, which is the same tree. So at least in the list we have done first six problems from the list today. So this is the latest list that I just pinged today. We have done the starting six questions from there. So I would like you guys to try out at least three to four more problems from that list, maybe in the same order, so that we don't have to spend too much time. And when you come into the session, you can tell, like you can ping on the chat, or you can say that I have done this problem, so that and if everyone has done them, then we can just simply skip them. We don't have to discuss it in detail, so that will save time. uh, does that sound good, this approach? All right. um, cool. We'll just wrap up the session. So thanks